Hi students, the last two lectures we understood the basics of state space modeling and we applied those principles to simple mechanical and electrical systems. In mechanical system we took the mass damper and spring system, which is a second order system, and for electrical system we took RLC series circuit, and that is also a second order system. So in this lecture, we will try to extend those basics we learned to slightly complicated systems or systems with more number of elements or systems with higher order systems. Okay. So as a first example, I've taken this system, so which is having masses m1, m2, the dashboards or dampers p1, p2, and the springs k1 and k2. Okay. So of course this has got more elements than the system what we considered earlier. So as a principle, before modeling any system in state space, the first thing what you have to do is identify the input variables, state variables, and output variables. So we'll do the same thing for this case, this system. The input variables are obviously U1 and U2, which are the forces applied on mass M1 and mass M2. Okay. Please note that when you talk about the system modeling in transfer function, as a transfer function, we will consider only one input and only one output. But as I said in the first lecture, the advantage of state space modeling is you can consider multiple inputs and multiple outputs. Therefore, for this case, we have considered two inputs, U1 and U2, simultaneously. Therefore, the inputs are U1 and U2. Okay. Then, the outputs are the displacement of mass M1, that is Y1, and the displacement of mass M2, that is Y2. So Y1 and Y2 I am going to consider as outputs. Of course, there is another possibilities of outputs, that is the velocities of the motion of mass M1 and mass M2, or even accelerations I can take as outputs. But for this case, for this study, I am going to take the outputs as the displacement of mass M1 and displacement of mass M2, that is Y1 and Y2. Okay. Then the question is about the state variables. Okay, so in the last lecture, in the first lecture, I told you that the number of states is equal to the number of independent energy storage elements. I think I need to expand that explanation in this lecture, and we'll apply some extended principles or something I'm going to explain new here. So one thing is, if you look at this mechanical system given, the energy storage elements are M1, M2, K1 and K2. Yeah, you can say that number of states is 4. Rather than identifying the number of states like this, again we have to go back to the energy concepts. See, if there is a mass, the energy stored in that mass has got two components. One is the kinetic energy and the potential energy. Potential energy you might have studied as mgh or max, mgx, and therefore it depends on the position. Okay. Whereas the kinetic energy is half me square, you might have studied, therefore that it is proportional to the velocity. So the energy stored in the mass itself is dependent on two quantities. One is the position or the displacement, and the other one is velocity. So therefore, if you take a mass, there are two states associated with the mass itself. So the variables, state variables associated with mass m1 or y1 and the corresponding velocity dy1 by dt. Okay, and similarly, the states associated with mass m2 are y2 and the associated velocity, that is dy2 by dt, its velocity. Okay, so we have got four state variables now. Now let us come to the other energy storage element K1 and K2, that is the springs. The energy stored in this spring K1 depends on this velocity displacement y1. Okay, so and this energy stored in this spring K2 depends on the displacements, otherwise the difference in the displacements y1 and y2. So the springs have the state variables, associated state variables as y1 and y2. This mass is having y1 and its velocity. So this is having a state variable as y2 and its corresponding velocity. Since the state variables associated with the springs are already covered in the mass, it need not be repeated. Okay, so therefore, ultimately, the state variables associated with the system are y1, dy1 by dt, y2 and dy2 by dt. Okay, so these are the four state variables associated with the system. Please note, since y1 is already associated with mass m1, you need not take y1 again as a state variable corresponding to k1, and similarly, since y2 is already associated with m2 as a state variable, you do not take y2 as a state variable corresponding to k2. So ultimately there are four state variables. Okay, so this first step is over. First step is identifying the input variables, output variables and the state variables. Now the next thing what you have to do is you have to write the equation for corresponding to the system. For any mechanical translation system, what we do is we draw the free body diagrams. So if you take the mass m1, the applied force or the exciting force is m1. Yeah, m1, the applied or the exciting force is u1, and these are the reaction forces. Reaction force due to m1, b1, reaction force due to k1, reaction force due to b2, and reaction force due to k2. And similarly, for the mass m2, the reaction applied force or the exciting force is u2. Okay, and the reaction forces are due to mass m2 and b2 and k2. Okay, so I have used this notation of here I have used it as y1 minus y2. So this displacement has to be taken as larger than this y2, and here when I take for b1 and k2, I have taken as y2 minus y1 because I am writing the expression for m2. So having drawn this free body diagrams, we can immediately write the equations, differential equations using Newton's third law, that is applied force is equal, sum of the applied force is equal to sum of the reaction forces, and we can write these equations for mass m1 and m2, and we can get two differential equations. We just see, we'll write those differential equations and we'll see how we can proceed to find out the state equations. These are the two differential equations we get from the free body diagrams. So the first equation is the one corresponding to the mass m1, and the second equation is the one corresponding to the mass m2. So these are all the reaction forces, sum of all the reaction forces on mass m1 is equal to the applied force u1, and sum of all the reaction forces in mass m2 is equal to the applied force u2. So we got the differential equations describing the system. And we have already defined the state variables. We have chosen the state variables, that is y1, dy1 by dt, y2, that is a displacement of mass m2, and its velocity dy2 by dt. So we have got four state variables: x1, x2, x3, x4. Okay. So having defined the state variables now, we need to get the state equations. What are the state equations? State equations are nothing but the equations which describes the variation of the state variables with respect to time. dx1 by dt, dx2 by dt, dx3 by dt, and dx4 by dt. Okay, so these are the state variables. These are the terms which describes how the state variables vary with respect to time, and these equations are known as the state equations. If you look at how we have defined the state variables, you can easily find out this dx1 by dt and dx3 by dt are already there. So dx1 by dt is nothing but x2 and dx3 by dt is nothing but x4. So you are able to see here this dx1 by dt is equal to x2 and dx4 by dt is equal, dx3 by dt is equal to x4. So among the four state equations, we have already obtained two state equations, dx1 by dt and dx3 by dt. Okay, so now our task is to find out the other two state equations, that is dx2 by dt and dx4 by dt. So to find these two state equations, we will make use of this differential equations obtained from the free body diagram. Okay, so simply they have been rewritten. These state differential equations are rewritten here. Only thing is, this single term is made into two terms, that's all. So here also it has been made into two terms, and k2 also is multiplied into y1 and y2. So that is the only modification done here. Now what I will do is, I will make use of these state variables x1, x2, x3, x4 and rewrite these equations. Okay, for example, this y1 is x1, so I'll just replace that y1 by x1. y2 is x3. Okay, so I'll replace it by x3. What is dy1 by dt? It is x2. What is dy2 by dt? It is x4. So they are accordingly replaced. And what is this term? This term can be written as d by dt of dy1 by dt. What is dy1 by dt? It is x2. So therefore this term can be written as d by dt of x2 or dx2 by dt. Okay. Similarly, we change the terms in the second equation also. We get this equation. If you observe this equation, it is interesting to note that we are almost to get this state equations dx2 by dt and dx4 by dt, because that is the only differential term in this equation, in these equations. Okay, so with a little bit of algebraic manipulations, we can get these equations dx2 by dt and dx4 by dt. Okay, yeah, we got it. So do a little bit of algebraic manipulations, we can get these equations. Sorry, yeah. So from this equation, what I do is, other than this term, all the terms are brought to the other side, and after bringing to the other side, the elements, the terms are combined. For example, this k1x1 and k2x1 terms are combined to get k1 plus k2 into x1. Of course, when they move to the other side, they will become a they will become a negative terms, and therefore this negative sign comes here. So k1 plus k2 into x1, and to have only this dx2 by dt term on this left side, m1 is also brought to the other side. So when it goes to the other side, it becomes a division, that is m1 comes here. So this term is k1 plus k2 by m1 into x1. Okay, and similarly x2 terms are combined together. So here when it goes to the side, it is minus b1 x2 minus b2 x2. So the negative sign can be taken outside, and it is b1 plus b2 into x2. This m1 brought to the side, it becomes b1 plus b2 by m1. So similarly x3 term is minus k2, and it goes to other side, it becomes plus k2, and m1 is divided, and k2 by m1 you get. Similarly x4 term, and regarding this u1, it remains positive because it is on the right side already, and only thing is you have to divide it by m1, so you get 1 by m1. Okay, so that is how you get this equation. Similar manipulations on this second equations will yield dx4 by dt. So that is in the order of the state variables x1, x2, x3 and x4. These are the terms. Okay, so the other two state equations also we have got. Okay, so these are the two state equations we needed, and those two equations are ready with us. So the final state space equations are this. Okay, so the four state equations are dx1 by dt is equal to x2, and this is dx2 by dt, and this is dx3 by dt, this is dx4 by dt, and so on. Okay, we got all the state equations now. This four state equations can be put in a matrix form now. Okay, so I'm going to do that. Yeah, so when I put this four state equations in matrix form, I get a single matrix state equation. This is going to be the final state equation. So it is in the first equations only x2 term is there. So this is a state vector, actually x1, x2, x3, x4. The coefficient corresponding to x1 is 0 because there are no x1 terms here, and x3, x4 terms are also not there. So therefore the corresponding elements in the matrix row will be 0, 0. We have got only x2, and therefore it is 1. So similarly this x1
for the second equation is the x1 coefficient is minus k1 plus k2 by m1 and so on. So we put all the coefficients of x1, x2, x3 and x4 and we get this matrix. And of course regarding this input terms, in the first equation there are no input terms, so the first row will be 0, 0, and in the second equation we have got only u1 term, so u1 is the first element and therefore the first element of the second row will be 1 by m1, and in the third equation there are no u terms. In the fourth equation there is u2, so the second element in the last row becomes 1 by m2. So we write this state equations as a matrix equation, and this is the final state equation. Now we have to get the output equation. Okay, so we already defined the outputs, that y1 and y2 are my outputs, and y1 and y2 are nothing but x1 and x3. Okay, so this is how we define the state variables. X1 is y1 and x3 is equal to y2, or otherwise y1 is x1 and y2 is x3. Okay, so this equation also can be put in matrix form. y1 is equal to x1, 1 into x1, all other terms will be 0, and y2 is x3, these two are zeros, and 1 into x3, that is 1 comes here and the element corresponding to x4 becomes 0. Okay, so this is the matrix form, and of course u1 and u2 will have 0 coefficients because there are no u1 and u2 here. So this equation is what we call it as the output equation. Okay, so we got both the state equation and the output equation, we write them together. Okay, so this becomes the state space model of the given system, where the state equation and output equation are written together. Okay, so now we will compare this state equation we have obtained with the standard form. Standard form is x dot is equal to ax plus bu and y is equal to cx plus du. They are nothing but the state equation. Okay, it's the standard form of state equations. So here A is this matrix, x is the state vector, and this is what, and B is the input matrix. This is what is the input matrix here. U is this input vector. Okay, so it's clear. And now when it comes to this output equation, Y is the output vector, C is the output matrix, and D is the feed forward matrix or feed through matrix. Okay, feed forward matrix, and of course this is input vector. Okay, now we'll just take some time to examine the size of these vectors and matrices. We know that the number of inputs is equal to 2, number of state variables is 4, number of outputs is 2. Okay, now if you look at this input vector, U is a 2 cross 1 matrix because there are only 2 inputs. So in general, the inputs, number of inputs is represented by R. So R cross 1 will be the size of this input vector. And state vector is this one. since we have got 4 state variables, the size will be 4 cross 1. And if you say n is the number of state variables for the system, the size of the state vector is going to be n cross 1. And the output vector is this one, y1, y2. So there are 2 outputs, therefore the size of the output vector will be 2 cross 1. And if I say the number of outputs is m, then the size of the output vector is going to be m cross 1. Now let us look at the matrices. State matrix A, this is the state matrix A, and of course this is going to be a square matrix always of the size equal to the number of the state variables, n cross n. Size of the input matrix is given by n 4 cross 2. You'll be able to see the number of rows will be equal to the number of states, and the number of columns will be equal to the number of inputs. So the input matrix size is 4 cross 2, or in general n cross r, where n is the number of states and r is the number of inputs. Output matrix is this one. You can see that number of rows is equal to the number of outputs, whereas number of columns is going to be equal to number of states. For our case, the size is 2 cross 4, or in general I can say m cross n, where m is the number of outputs and n is the number of state variables. And the feed forward matrix D, this is the one, and you can see the number of rows is equal to number of outputs, and number of columns is going to be equal to number of inputs. So here we have got the 2 inputs and 2 outputs, therefore the size is 2 cross 2, and m cross, there is a mistake, m cross r. This should be m cross r. Okay. So you will be able to see that among these matrices, only the state matrix is going to be a square matrix. All others are going to be rectangular matrices. They can be square matrices also, but they need not be square matrices. For example, in our case, the number of inputs and the number of input is 2, so we got the matrix D as a square matrix, but it need not be true always. The number of inputs and the number of outputs need not be equal. Okay, so that's the point. Anyhow, the important point is the state matrix is always going to be a square matrix. And you need to note that matrix D can be called as a feed forward matrix or feed through matrix, or sometimes it is called as direct transmission matrix also. So in this lecture we took up a problem, an example problem containing 2 masses connected with various elements, and we understood how to get the state space model for the given mechanical translational system. Okay. How did we start? We'll just go back, we'll just revise. We drew the free body diagram, and we also identified the input and output variables along with the state variables. Then we defined the state variables. Then the state equations were written. The 2 of the state equations we could get directly from the definition of the state variables, and then from the differential equations we could get the other 2 state equations. So all the state equations were combined and they were written in a matrix form. Now we have to get the output equation. Outputs were defined and they also were written in a matrix form, and the state equation together with the output equation gives you the state space model, and we compared it with the standard form, and then we defined the size of the various vectors and matrices in the state space model. So here we end this lecture, and in the next lecture we will see how to get the state space model of an electrical system with more than one loops and more than two energy storage elements.